In this session, we will continue talking about pretty well one of the most basic assumptions within quantum mechanics, one of the basic postulates, and that is we're heading towards a generalization, which I've put here. We've done it in the case where your observable, remember an observable is a physical quantity that you can measure, so a measurable physical quantity, for example the position, the momentum, angular momentum, spin. We haven't done spin yet, but it's coming, stuff like that. So let's generalize, and this is where we're heading, and this session, the next few, will be showing that this idea. We talked a little bit about these two main things we had to keep in mind at the end of the previous session. So I'll put them up here again, and I'll go through them again because they're really important, essential to understanding what quantum mechanics is about. But for these sessions, the observable will be energy. Now, before our observable was position, measuring the position of a quantum system, a particle in a box or whatever. And this time it'll be energies, particularly in the case of the infinite square well, as you'll see in the coming sessions. So I'll try and reinforce the idea, because it's really basic. You know already that in quantum mechanics, observables can often take on quantized amounts. Like when you measure some quantity, some observable, often you'll get only discrete, allowed measurable values, measured values. For example, like energy, you only get certain discrete energy, allowed energy levels. Or next chapter when we do angular momentum, you'll see there are only discrete, allowed angular momentum values and stuff like this. So for each allowed value of something that you measure, so for each observable's allowed or discrete measurement values, whatever they are. So if we generalize it a bit, so let's say we're talking about observable A, big A, where A might be position, momentum, angular momentum, energy, whatever, okay? And assume these allowed values are discrete, okay, quantized. That's what we're talking about, quantum mechanics, quantized mechanics, the essential idea of quantum mechanics, okay? And when you measure that observable and you get discrete measurement values, quantized values, and let these values be a range of them, and let them, these actual the results of your measurement, the measurement values, be of this form. Like A1, A2, A3, whatever. Like this might be angular momentum 1, 2, 3, whatever, or energy level 1, that would be the ground state, the lowest energy, E1, E2, E3, dot, dot, dot. So generalizing it to form AI. Then, now this is the mathematical symbol, you've probably seen it before. It looks like a capital E, but mirror imaged. So in mathematics it just means there is or there are. Okay, so for each one of these discrete allowed values, results of the measurement, there's a corresponding eigenfunction. So for measurement value AI, and little AI is an allowed value, a discrete value that you get when you measure observable A, and generalizing here. Okay, then corresponding to that allowed measurement value, there's a corresponding wave function. And one of the basic assumptions of quantum mechanics is that these wave functions that correspond to these discrete allowed measurement values are orthonormal. Right? Now, what I just said is really important and pretty much the heart, well, one of the major concepts of quantum mechanics. So I'm really trying to emphasize it. Okay, so these eigen, well, I keep using a term, I haven't quite got there yet. These wave functions that correspond to the allowed discrete measured values, they are orthonormal. That's the assumption. So your bracket of two different ones of these will be orthogonal, meaning this bracket or the overlap integral, same thing. It's just writing the overlap integral in a different way. This is Dirac's, Paul Dirac's bracket, bra. The left one's the bra, the right one's the ket, bracket or bracket notation. Right? And so the bracket is just the delta function. So this is either 1, if I and j are the same, then this wave function, it's not only orthogonal to all the other wave functions that correspond to different measured values, right? But they're also normalized. So if you bracket it with itself, if I equals j, you just get 1. Okay? So let me say that again, just for emphasis, given its importance. You measure some observable A, right? Might be you're measuring the energy, the momentum, angular momentum, whatever. Okay. And let's say you obtain a value in the measurement, a little I, and this little a corresponds to your big A, the observable you're measuring. Corresponding to that measured value, you'll have a corresponding wave function called, let's say, psi of I, where this is the ith allowed value that you can measure, assuming this observable here has only discrete allowed values. So it's quantized. It's a quantized quantity, observable, right? Then these wave functions here are orthonormal, right, relative to the other possible ones. So if you get the result AI, then for any other possible result, say AJ, you'd have a corresponding psi function psi j. So if you take the bracket, if you take the overlap integral of your psi I, the one for which you got a measurement result AI. So if you then bracket psi I with any of the others, psi j, you'll get delta ij. And if I and j are different, this will be 0. And if they're the same, this will be 1. So this is the Kronecker delta, right? And this is your bracket, or expressed otherwise, the overlap integral, right? Okay, so that's basic. Now there's another basic one. So these two are part of the heart, the conceptual heart of quantum mechanics, and hence very important. So really master this stuff, because you'll carry these two assumptions forward for the rest of the course, and the rest of your careers in quantum mechanics. So this is sort of the core, okay, or one of. All right. Okay. So you've got these eigen. I keep using that term. I'm so used to it because that's what they are. Yeah, but we haven't got there yet. These wave functions that correspond to the allowed measured values, right? And these values turn out to be eigenvalues as well, but I'm getting ahead of myself. So you can take, now remember, we're talking about these two things are situated within the context of superposition, right? So superposition is one of the most basic concepts in quantum mechanics. If you have one solution to the Schrodinger equation, psi 1, and you have another solution to the Schrödinger equation, psi2, then any weighted sum, so like C1 psi1 plus C2 psi2, C1 and C2 are just complex numbers, then that weighted sum is itself a solution to Schrödinger's equation. So you have this sort of a general superposition form. So if these psi i's, these wave functions here that correspond to the allowed measured values, discrete values, then you can express a general wave function in terms of a superposition of these wave functions that correspond to the. So if the state, for example, is in this state and not in a superposition, so it's just in this pure state in a sense, then if you measure the observable A when it's in this state, for sure, with 100% probability, you will get this result, AI. But when it's in a superposition state, like this, and this is part of the quantum mechanical model, right? So when psi is a superposition of this form, then after you do the measurement, this psi will now collapse. The resulting state will be one of these wave functions here, and let's say the result that we got when you do the measurement is a little I. So this is one of your discrete allowed measurable values. Okay. So if you get that one, its its wave function that corresponds to this measurement is this one, let's say. So your psi now, which was a superposition, collapses to that wave function that corresponds to the value that you obtain, AI. Okay? And the probability that happens, that this collapses to that you get this result, AI, the probability that happens, remember talking quantum mechanics, probabilities, another basic notion of quantum mechanics, determinism out the door. It doesn't work in, well, under certain circumstances it works, but in